Okay, I want to welcome everyone to my lecture today. I also need those of you online to confirm if you can hear me clearly. Those of you online, can somebody confirm if you can hear me clearly? Okay, thank you so much for confirming that. Um, Today, we actually going to continue from, where we actually stop on Wednesday. On Wednesday, we started what I call repeated measure ANOVA. Of course, in today's discussion, we're going to focus on, you know, what is the consequence of ignoring a correlation problem. Okay, so we're going to look at the consequence because we know that when we are using repeated ANOVA measure, we are, the subject are visited in a multiple occasions, we expect the response to be correlated. Now, if we ignore that and we decide to use statistical approach that assume independence, then what would be the consequence of that? So that is going to be the focus of our discussion today. Now, looking at the outline, of course, like I said, we're going to discuss correlation problem. Then we're also going to see in today's lecture how, what would be the consequence, of ignoring a problem, when there's a problem. So which means if assumptions are violated, so what is the consequence of that, with regards to repeated ANOVA measure? Okay, I'm going to discuss that. And I'm also going to walk you through illustrative examples. But before I go into the topic of the day, I think I would like to have a recap, for those of you who are actually attending repeated ANOVA measure for the first time. In statistical analysis, if we want to compare groups, why do we need to compare groups? Of course, we live in a stochastic environment. There's a lot of variation. If there's no variation, we don't need to compare any groups because every item, every unit will also be in the same group. But it is not like that in a probabilistic world. And we now want to, if we want to compare groups, of course, if the groups are independent and they are two in number, of course, we use a two sample t-test. And that's actually come with assumptions that, each group must follow normal distribution. Not only that, they have to be independent, among other assumptions. And of course, in a situation where we got more than two groups, okay, and they are independent, and we basically want to compare on average whether the response is the same, okay, of course, we're going to use our ANOVA. We're going to use analysis of variance. But using analysis of variance, assumption is that the participants in our cohort, they were only visited once. So the fact that they were visited once, we already we've already secured the assumptions of independence. And that is the reason why we've not been tested whether assumptions of independence hold. We've not been testing whether assumptions of independence hold because the mode of data collection, we use what I call the principle of randomization. That assumption is already secured. Using the principle of randomization and using the fact that we only visit the respondent, the participant, in only one occasion, that has already secured independence assumption. We don't need to investigate that. Now, in a situation where the participants were visited in two occasions, let's say only two occasions, okay, and then we will actually want to, test and compare means. Of course, that would be a paired t-test that you're actually going to apply for that, okay. But what if in a situation where we got more than two dependent groups? Okay, I'm going to say that again. We have more than two dependent groups from three dependent groups and above. What's actually determining the dependency now is the numbers of occasions the participants were visited. If the participant were visited 3 times, then you're basically going to have three dependent groups. If they were visited 4 times, you're basically going to have four dependent groups. And in a situation where we got, more than two dependent groups, then we are automatically talking about repeated, ANOVA measure. Does that make sense to everyone? And of course, I gave an example the other time, when you are trying, when a doctor is treating some patient, maybe they play sports and they have a knee injury, okay, and they want to operate on their leg. They want to conduct what I call a surgical operation. If the doctor decide to, want to compare the perception of, patients, or a pain, okay, maybe before the surgical operation and after the surgical operation, okay, if the doctor only investigate, the perception, okay, of a patient, level of, of pain, okay, in only 2 occasions, of course, we're basically going to use a sample t-test, okay, don't forget we're using the same subject. And what if the doctor decided to do that in 3 occasions, maybe before the operation, in the middle of operation, and after operation? That means the subject, the patient this time around, they were visited how many times? They were visited 3 times. So when they were visited 3 times, we are automatically creating three dependent groups. It is called dependent because, of course, you are getting, three different responses from the same individual. Now, I use that example in, in medical line. I also want to use another example in marketing. For instance, if I want to know every companies, that sale, they basically want to measure maybe their customer, the perception of the satisfaction, of the customers. Maybe at one time they conducted a survey on some people that buy from them about, they ask them about whether they render good services or they sell good products, you get what I mean? And they record that. Maybe they visited them in another occasion to be able to ask, because as if you have a company, if your customer tell you in one occasion that your product or your service are fine, okay, you need to revisit them again because things change. Okay, so when you revisit your customers in more than 2 occasions, it is the same customer, okay? It is the same customer that you are focusing on. That's another example of a repeated ANOVA measure. But you know what we want to do in today's class? In statistical analysis, if we want to model the world, if we want to capture reality, we cannot capture reality exactly. Why? What makes it difficult for us to be able to capture reality exactly is because of the fact that the model that we use in statistics is probabilistic. I'm going to say that again. Statistical model cannot capture exact reality because of the fact that the model we use is probabilistic in nature. What make a model? What make a model probabilistic? Because in our model, there's a random component. There's always going to be a place of unexplained variation that we call error, that we basically want to minimize. And no matter how we try, it can never be zero. Now, every assumption, that's, of any statistical model revolve around the error term. I'm going to say that again. Every assumptions, okay, that underline the use of a statistical model revolve around the error term, which I call the unexplained variation, okay? And that is the reason why we need to be able to investigate whether assumptions hold before we can validate or trust a model. If assumptions do not hold and we ignore that, we're actually going to mislead. And that is the reason why at times it's going to look as if our models are failing us. Our models are not failing us. We are the one that we're not doing the right thing. Maybe assumptions are violated, we ignore that. Or even, I know there are some of researchers that don't care. They don't even investigate at all, forgetting that a model is as good as assumptions putting into a model. Now, let me tell you this. With the repeated measures ANOVA, because the same subject were visited, so many times, then one assumption is already violated, which is assumptions of independence. Okay, which means when assumptions of independence is violated, it means there's a correlation problem. And that is what we want to look at today. Like, okay, if I ignore correlation problem, what happened? Let me just tell you the secret. If I ignore any violation of assumption, it will tell on the error term, period. I'm going to say that again. If assumption is violated, it will tell on the error term. The error term in the model that you are trying to minimize will be maximized instead of minimizing. That is just the bottom line. Okay, so I'm going to of course, I just talk about this guy now. Repeated measuring the same individual. We produce correlated data. I think I just mentioned that. And that will lead to a violation of assumptions of independence. Let me tell you this. Most of statistical tests rely on independence assumption. I'm going to say that again. Most of statistical tests rely on independence assumption. That very assumption is critical in any statistical finding. And that is the reason why, if we don't want to mislead, okay, we need to be able to investigate that assumption. And if that assumption is violated, then we need to try a different method, or we fix the problem if we don't want to mislead. Now, and I said, if we ignore the correlation and pretend that all the data are uncorrelated, when data are uncorrelated, they actually means they are independent. Okay, then what are we going to have? What is the consequence? We misrepresent the amount of information we have, and the analysis will be flawed. We don't want that. We want to guide against that. Okay, now, do you know that it is not only assumptions of independence that will be violated when you are dealing with a repeated measure? Assumptions of constant variance too will be violated. Maybe in the first occasion to a particular, maybe from one occasion to another occasion, the variance may not be the same. And that was why I said the variances may not be homogeneous over the entire duration. There are some patients, there are some participants that they were visited in even 6 occasions. All what we're trying to say, homogeneity of variance is not guaranteed over the period of time the participants were visited. And of course, the variability of the response at the end of the study is often very different from the variability of the response at the beginning of the study. That's why time is very, very important. Oh my God, another assumption is violated. Number one, independence assumption violated automatically. The second assumption that is violated is a cost time variance. These two assumptions, they are key. Okay, we want to go into treatment of lead exposure. Like I want to have this, like having so many examples of repeat where we can actually use repeated ANOVA measure. Okay, so I give a lot, but I'm actually going to focus on the last one. Okay, we're going to focus on the last one where we measure blood lead levels as baseline, week 1, week 4, week 6. You know, the baseline is basically you're going to serve as a control. Okay, so take a look at that. Now week 1, week 4, so we're making 4. We're actually talking about 4 period. Let's take a look at the data. Right here, you know, I'm actually going to call this two-way, okay, a repeated ANOVA measure. Why do I call it two-way? I call it two-way because the first factor is time. I told you, automatically, when you are working with a repeated ANOVA measure, the first factor is time. Because the time become a random variable. Because you did not visit the participants in only one occasion. The participant were visited in more than one occasion. The first factor is actually time. But the second factor that I'm seeing on the board is the treatment. We got 2 levels of the treatment. The placebo and the Sosima. Take a look at that. The placebo and the Sosima. Take a look at that. We got 2 levels of the treatment. The factor B in this study is a treatment. The factor A in this study is time. How many levels of time do we have? We got 4. Take a look at that. Any question on this data layout? Any question? Is there anyone who need a clarification on understanding this data? Because in exam, what if you're given a data structure and it's okay, figure out what do we mean here? Can you tell us the appropriate design? When I ask you what is the appropriate experimental design here, this is a two-way ANOVA with a repeated measure. A two-way ANOVA with a repeated measure because you got more than, you know, the participant were visited in more than one time. Y0 is the baseline. Y1 is another time period. Y4, maybe Y0 is week 0, week 1, week 4, week 6. Take a look at that. And we got 2 levels of treatment. One is an intervention, the other one is control. The one that is control is placebo. The Sosima is the main treatment. Now let us run a descriptive analysis now. We want to run a descriptive analysis on the 2 levels of the treatments. Oh my God, I basically want to see on average, you know, over time, you know, I want to compare the placebo with the Sosima. The placebo is doing nothing. It's like we know no intervention. That's a control. The Sosima is the treatment effect, like is a treatment that you're applying now, and you actually wash the participant over 4 period of time. you got two major group you of the participant. You assign participants randomly into two different groups. I'm going to say that again. You assign because you're using the principle of randomization. But if you did not observe them at different time period, independent assumption hold. I'm going to say that again. If you did not observe them at different time period, if you only focus on one time period, of course, independent assumption hold, because the way at which you assign participant to group, you do it in the way every group has equal chance, equal probability of receiving any participant. How many groups do you have? A placebo group and a Sosima group. Okay, you were not biased when you were assigning participants to the two groups. You use what I call the principle of randomization. But what makes assumption of independence to be violated is the fact that you observe the participant in more than one time period. I wanted to look at the analysis on the board. We're trying to get the means, plus or minus the standard error. Take a look at the Sosima. Okay, you have the mean to be 26.54 for Sosima. For placebo, the mean is 26.27. That is, you're looking at that in the first week of your study. The first week of your study. Okay, the average of the participants that receive Sosima, okay, the average of the characteristics of interest actually give you 26.54. But the average of those who do not receive the treatment, which I call placebo, is 26.27. Of course, we also get their corresponding standard deviation. We now get that for the fourth time period. What did you notice? Whether for placebo group or for Sosima group, you can see there's a change in mean over time. Take a look at that. The Sosima group go from 26.54 average in the first week to week 1 to 13.52, later increase in week 4, and also increase in week 6. But when you take a look at the placebo one, you see that? Any question on what I put on the board on this descriptive analysis? Any question? Any question? Okay, you're good, right? This of you online, can you confirm again? If you are hearing me clearly.
Yes,
Somebody's
I can hear you.
Oh, you can hear me. Thank you so much. Somebody said on the chat, somebody said on the table, what are the parenthesis values interpreted as? That's a very good question. The parenthesis values are more or less like the standard error. Okay, they are like the standard error because how can we tell about the reliability of the mean? In statistical analysis, where we figure out the mean, okay, we believe that the mean is representing, right? For us to be able to know that it's representing, in some occasion, we need a margin of error. You can't get to margin of error without getting a standard error. So what we're saying is that if you look at the Sosima in the baseline, that we have the mean of 26.54, what we are telling the world, it could go up by 0.71, it could go less by 0.71. So the person that asked that share with me online, I hope you get that information out. So when you are getting the average, we need something to tell us how reliable is the average. Okay, now take a look at this. I want everybody to be focused. Every question should be directed to me. Hello, can you hear me? I want everybody to be focused. No discussion. When you are done, you can discuss, okay? Thank you so much. I want everybody to be focused and get the information. Okay, now take a look at the plot here. This is more or less like you're plotting the response variable against time, and you overlay that. We started again. We overlay that with a categorical treatment factor. Take a look at this now. Okay, the broad lead is the response, and we got 6 different ways. Don't forget, we visited the participant in week 0, week 1, week 4, week 6. This particular graph now is a way to compare the 2 levels of treatment over the 4 weeks. Take a look at that. Okay, the Sussiman is in blue. The treatment one is in blue. The placebo is in red. Take a look at that. They don't have the same shape. Okay, over time, look at the spread of the Sussima. Look at that's of the placebo. Okay, take a look at that. Now, I want us to focus on what I want to, because I realize my experience in teaching in Africa, Europe, and United States. I realize, I think the only place I've not touched is Asia. I would love to go to Asia one day. I've been seeing the continent. I like the continent. I'll visit there one day. Okay, so, but even though I've not been to Asia, I got a lot of Asian friends. So, they are very nice people. Everybody is nice. So variation is good, Without variation, no statistics. Without variation, the world will not be beautiful. Okay, now I wanted to focus on these notations now. Why is it that students offering mathematical related course, why do they have difficulty? They have difficulty because they don't relate notations to real life. I want you to pay attention to this. We're going to play with notations now. Now take a look at this. Let Yij denote the response. Okay, variable for the ith individual at the jth occasion. Look at the word Yij. I represent a particular individual. Okay, J represent the location. I mean, the occasion. Don't forget the occasion in this question is 4. But let's generalize. Like we have occasion from 1, 2 to n. I want you to see the table. This is a layout of a repeated measure where we got n individuals and they were visited in a good number of occasions. This is a general layout. Do you know that the first row is for the same individual number 1? The second row is for the same individual number 2. I want you to pay attention to that. Y11 is different from Y21. Y11 is the response that we got from individual in the first occasion. Okay, Y21 is another individual, but the same occasion. Any question? Take a look at the data layout now. Now, take a look at this vector notation now. Y high. This is like a response of a particular individual. Y high. When I say I equal to 1, that is individual number 1. Individual number 1. What this is now going to be the responses that I got in different occasions from individual number 1 when I plug in 1 for high. Any question? This is just a generalization. This vector is telling a story. This is a generalization of, when I say yi, could be any individual. And what you see in the vector is just the different responses that I got from the same individual in different occasions. Oh, I want to go mathematical now. Then I'm going to find the transpose of that, which is basically going to be that. So which means the mathematical way to put that, I can have it as a column vector. I can have it as a row vector. Okay, now we want to talk about correlation now. But do you know the correlation that we want to talk about? We only want to focus on a particular individual. Why are we focusing on a particular individual? Because more than one response is coming from an individual. And we expect those responses to be correlated. And that is the reason why we want to look at the correlation. And there's no way we can get to correlation without passing through variance, without also passing through the covariance. Of course, that is the reason why, and let me tell you this, I said when the covariance is 0, it means there's no linear relationship between responses at 2 occasions. That is when the covariance is equal to 0. Okay, now take a look at this now. I want to generate a correlation matrix. Oh my God, I'm generating correlation matrix for a particular individual. If you take a look at what I have now, I'm focusing on individual y high. Okay, and I basically want to have, what is the variance covariance matrix for that? Because when I get a variance covariance matrix, that will enable me to get a correlation matrix. What do I want to do? I basically want to have a way to compare, in pairs, the responses, okay, at different locations for the same individual. Any question to this notation on the board? Any question? What are we focusing on? We're focusing on one person. One person. Okay. Now, what I want to do now, because we are having 2-factor, right? In this repeated ANOVA, I'm going to remind you about the 2-factor. The first factor is the time component, and the levels of that is 4. They were visited 4 times. And the other factor is a treatment factor that has 2 levels. Okay? And don't forget that there could be interaction because we get 2 factors, right? Because there's possibility that behavior of a treatment may depend on time. Okay? If, of course, interaction effect becomes important if maybe factor A is not consistent. Maybe the behavior of factor A, okay, depends on it's not the same when you put into consideration the levels of factor B. What am I talking about? Maybe the treatment effect or the placebo effect depends on time, period. And that's why interaction is going to come in. Okay, now when we plot that, so we can actually have a plot for that. Give me 1 second. Now, the next thing I want to go into now is the correlation matrix. As you can see, don't forget, this correlation matrix focuses on an individual. If I have 10 individuals, I'm going to have 10 correlation matrices. If I have 15 individuals, I'm going to have 50 correlation matrices. Of course, I expect the diagonal of the correlation matrix to be 1, 1, 1, right? So take a look at that. And of course, we expect it to be symmetric. What do we mean by symmetric in mathematics? When you transpose this, it's going to be the same as this. Okay? So take a look at that. Now, coming back to the example at hand on the treatment of lead exposed children trial, don't forget, we got 2 levels of treatment, the placebo and the sorcerer, and at 4 different times. Okay, we can actually get a scatter plot. If you take a look at the code here, scatter plot library lattice, okay, PS, okay. If I want to focus on the baseline, okay, let's look at baseline at different time point. Do you know what is this scatter plot giving me? This is just a scatter plot. Okay, you know, we are only focusing on one level of a treatment. What was that level of a treatment? A placebo. We're looking at that in relation to week 0, which is a baseline, week 1, week 4, week 6. From what I'm seeing here, this is looking like there's a relationship. Take a look at that. But if you really want to know more, you can look at the correlation matrix. Oh my God, look at the correlation matrix now. It's 0.82. Those are very, very high. Do you see that? The correlation that we have are very, very high. Okay, they are very, very high. So that is an indication of a clear of violations that I talk about. Here, I'm only focusing on the placebo, okay, group. You can do the same to the treatment group. Okay, now this is what we observe. Correlations are positive, of course, as you can see, the correlations are positive. Okay, the correlation decrease with increasing time separations. Correlation between repeated measure rarely ever approach 0, and correlation between. So these are just like what we observe, in this correlation matrix, and the same thing. Like, take a look at that. That's what we observe. Take a look at that. Now, let us now examine the consequences of ignoring correlation. Okay? Now, you know what's going to happen? Let's say, for instance, we only want to focus on the placebo group, and we want to look at the difference in the response between week 0 and week 1. I'm going to say that again. Is there a significant difference in response between week 0 and week 1 in the placebo group? You can also do that for the treatment group. In statistical analysis, for those of you online, if you are not seeing the board, I'm going to write something on the board now. So I need you to tell me if you are not seeing that. If I have x1 minus x2 in statistical analysis, and x1 follow normal with mu1, okay, and sigma squared, and x2 follow normal with mu2. Why do I write sigma squared, sigma squared? I'm assuming a constant variance, right? I'm assuming there's no violation, right? If I want to get the variance of this guy, oh, I'm doing statistical theory now. If I want to do the variance of this guy, it's going to be variance of x1 plus variance of x2 minus 2 covariance, x1, x2. But if x1 and x2 are independent, you know what's going to happen? This guy should go to 0. Does that make sense? Now, we are now, so that's why we actually make use of this. Even in your t-test that you always do, if you have x bar 1, you normally look at this. If you want to look at this, if I want to find the variance of this guy now, it's going to be variance of x bar 1 plus variance of x bar 2 minus 2 covariance x bar 1, x bar 2, but you have already made an assumption that S1 and S2 are independent. This is going to go to 0. And if x1 follow that, x2 follow that, of course, x1 bar will follow, that with mu1, but we're going to have sigma square n. And x2 bar follow that with mu2 sigma square n. So let's say, for instance, let's say sigma 1, sigma 2 here. That is why you normally have this divided by this. Do you remember t-test that you always do? This is how they derive that. They are assuming that the covariance equal to 0. They are assuming independence. Okay. Now, what is the takeaway? If it is not, if they depend, and you assume that they don't depend, okay, what will happen? You are assuming this to be zero. And if this is not zero, okay, what will happen to this variance? Can somebody tell me? Can somebody tell me? If the covariance, based on what you see on the board, if the covariance is not zero, if this guy is not zero for extra credit, if this guy is not zero, okay, what do you expect for this? Is this guy going to go up or go down? Can somebody tell me? If this is not zero, if this is not zero, can somebody tell me? It's going to what? It's going to go down. Send me a message for extra credit. So which means if you ignore, like if this is real and you ignore that, you will not minimize this guy. The only way you can minimize that variance of the difference is when you take into consideration the values of the covariance when they depend. Does that make sense? And that's exactly what I'm showcasing here. Take a look at this now. The variance of the data. What was the data? The data is the difference between means in two occasions. What are the two occasions? The week 0 and the week 1. Okay, and of course, you know, if I want to find the mean, it's a 1/n summation yij. Now, when you subtract the two mean, you know, the other time we got the mean, right? We got negative 1.61. If you want to get the variance, of course, take a look at that. 1/n sigma 1 squared is the variance of x1 that you see. Sigma 2 squared is the variance of x2 minus 2 covariance is 2 sigma 1 2. Now, when you calculate the covariance, okay, do you see that? What was the variance of the data? Is 0.19. When you did not calculate that, when you ignore that, what is the variance of the data here? When you ignore the covariance, what was the variance of the data here? 1.10. But when you don't ignore that, what was the variance here? It's 0.19. You can see now the variance go down when covariance exists and you don't ignore that. But if covariance exists and you ignore that, then you are not able to minimize that. Okay. Oh, somebody online also chat with me and said go down. Okay, the person online send me a message for extra credit too. Okay, send me a message for extra credit. The person that said go down, I need the person to confirm what I'm saying now, to be able to know the person is still around. I need the person to confirm. The person that said go down, I need the person to confirm now before I'm actually, because okay, good job, just confirm that. Send me a message for extra credits. Okay, now what is the implication now? The variance is affected where you ignore. Okay, and in statistical analysis, variance is very, very important, because when you get the variance, don't forget we need a standard error, right? The standard error depends on your variance. And if the variance is large, what happens? The standard error will be affected. When standard error is large, oh my God, what will happen to the margin of error? Because if you want to get a margin of error, you need a standard error and a quantifier when the standard error is going to go up. When the standard error goes up, oh my God, what will happen to the confidence interval? The confidence interval will be wider. When the confidence interval is very wide, that's a problem. And that was what I said here. The consequence, the implication now of ignoring correlation problem is the standard error will be too big, because the variance is already big. The confidence interval will be too wide. What makes the confidence interval to be too wide is because of the fact that the margin of error is wide. And what made the margin of error to be wide is because of the fact that the standard error is large. What made the standard error to be large is because of the fact that the variance is large. Look at the story. And if the standard error is large, if I want to conduct a test on the difference in the response between week 0 and week 1, what will happen to my p-value? My p-value will be large. Well, sorry, will be very, very large. And you're going to see now. You're going to see something now. How do I know my p-value is going to be large? You're going to see now. Because when you are conducting a t-test, right? When you are conducting a t-test, you always do something like this, divided by maybe this guy, right? Okay, when this guy is large, when this guy is large, what will happen to t-value? The t-value will be very, very small. When your t-value is small, your p-value will be large. I'm going to say that again. When your t-value is, what make your t-value, your test statistic value to be small is because of the standard error is large. Imagine the denominator of a fraction is very, very large. What do you expect the whole fraction? It's going to be very, very small. And when the t-value is very small, the p-value will be large. Don't forget, you want to compare the p-value. You want to compare the p-value with the level of significance alpha. When this guy is large, right? There is possibility you're actually going to fail to reject the H0. Even though if difference exists, if naturally differences exist, that may lead you to reject HO because of the fact that the p-value is large. And what makes the p-value to be large is because the test statistic, look at the story. What makes a p-value to be large? Because mathematically speaking, the test statistic value is small. What makes it a test statistic value to be small? Because the margin, because the standard error is large. What made the standard error to be large? Because the variance is large. Because if you want to get the variance of the difference of means, of course, if the two means or two variables depend, you need to subtract the covariance. You need to put into consideration the covariance. When you ignore that, it will affect your variance. When it affects your variance, it affects your standard deviation. It affects everything that you're basically going to do that depends on the variance. That is what we mean. Any question? Any question? And that was why I said in general, failure to account for the correlation or covariance among the repeated measures will result in incorrect estimates of the sampling variability and can lead to quite misleading scientific inferences. We've witnessed this, some of this, most of the time, where researchers don't really care about investigating whether assumptions hold. Assumptions are very, very important. It's more or less like I want to drive in the state of Minnesota and I decided not to obey the traffic rule. Of course, I know the consequences. It's either I'm actually going to involve in a crash or I get ticketed by the police. And some people will say, oh, yeah, I've been doing it and I don't get caught. The fact that you don't get caught does not mean one day, if police don't arrest you, the nature will arrest you. That is just it. Though the most important thing is do the right thing at the right time. That's what we mean. Any question? Is today's topic interesting? Do you want to take more of statistics? Statistics is very, very easy. The only thing you just need to do with the statistics is just to relate to real life. That is the way I understand my statistics and maths. I want to be seeing what I'm learning. If I don't see it, I don't like learning abstractly. It doesn't make sense to me. What is the essence of coming to college? Oh, because I want to solve a problem in the society when I join the larger society. I want to, when I join a Liar Society, I want to solve a practical problem. Then I need to understand what I learned in college practically, because I'm still going back to the Liar Society. It's another Friday. Make sure you stay safe and have a lovely day. Bye for now, everyone.